physics from the State of the University of Rio de Janeiro, and I bring on this poster for you some interesting results that we found at the end of the PhD work and are being submitted for publication. The work is carried out by your research group composed of the PhD Henrique Oliveira and PhD Williams Barreto. It's well established in the academic literature that the fluctuations or inhomogeneities of the inflaton scalar field can be exponentially amplified in the transition period between of the ends of the inflationary region and the thermalization of the universe. Knowing that this amplification also induces the growth of the possible perturbations in the gravitational field that would briefly disrupt the linear region of the perturbations, our work investigates what the nonlinear dynamics of these gravitational components. In a way, from direct questions would be: do single self-interacting scalar fields models describe this transition phase of the universe without inconsistencies? Well, so that work could be made compatible with the most recent observational data. We found that models of this type, that is, single scalar field and self-interacting scalar fields, may be completely within observational predictions if there is a small change, the non-minimal coupling between the scalar field and geometrical scalar curvature, as can be seen in the data from the Planck collaboration in 2016. Starting from this point, we consider a general line element, as we can see in the poster, where alpha and beta, where coefficients depends on both time and space. And as a non-minimal coupling is inserted directly into the Lagrangian, the energy moment tensor takes on a new form, verified on the literature. Thus, together with the Klein-Gordon equation for the scalar field, we were able to obtain a set of 4 equations in addition to constraint equations to be evolved to analyze the dynamic behavior of the system. Noting that K is the extrinsic curvature and all the equations are already written in their dimensionless form. The integration of these equations were performed using the spectral method, more specifically the placement method. Since we are modeling the universe as a three-dimensional outside box with periodic boundary conditions, to solve the system we use a Fourier base. Thus, all relevant variables can be written approximately as a homogeneous part exclusively dependent on time, multiplied by inhomogeneous parts. As these quantities are physical and therefore cannot be imaginary, complex coefficients will have to safeguard symmetry conditions, give us a finite number of independent coefficients that help us to define the placement points in the grid integration. After the numeric integration, the graphs contained in figures 1 and 2 were obtained and analyzed qualitatively. In all of them, it is possible to notice that even with the non-minimal coupling term, the parametric resonance mechanism experienced by the fluctuations of the inflaton induces an exponential growth of gravitational perturbations. The coupling term has a discrete role, delaying the appearance of this effect. It is important to note that in all cases, regardless of strong, unreal, or weak coupled with observations coupling, the perturbations modes of the gravitational field go rapidly induced growth but stopped growing always stabilizing their amplitude by approximately 2 orders of magnitude less than the inflaton. Thus, we can conclude that, in addition to being an observationally viable candidate to describe the inflationary period, the single-field self-interacting model with non-minimal coupling also describes the transition from a cold and empty universe to a thermalized universe without any inconsistencies. This interesting model still has some possible observational consequences to be analyzed in the future works, like the influence of these effects in the equation states and amplification of primordial gravitational waves. Thanks, and good to see you.